welcome in EE-231 electronic devices and circuits. So 15 weeks lecture are going on, and in the last lecture we covered the introduction portion, and definitely starting with the review of data introduction portion, and also covered the fixed biased configurations. And in that case, when RS is equal to 0, so that is the case, and this is a self biased configuration, and the voltage uh, applied to the gate is due to the voltage 12 across the resistors RS, which is not 0 in this case. This is the self biased configurations, and definitely both cases can be discussed in the form of design. If we want to change the Q point for self-biased configuration, we have to change the value of RS. And similarly, for fixed bias configuration, if we want to change the Q point, we have to change the voltage of the DC source, which is supplying the voltage to the gate. So this is the simple introductory part, and definitely we will continue with the next topic. And in this lecture we target the CLO3 and CLO4. CLO4 definitely parallel will covers for in the design part also. And JFETs based circuits are the fixed bias, self biased, and the voltage divider, and the depletion type MOSFET based circuits are the self biased and the voltage divider bias circuits. And basically we have some specific relations, and for JFETs and depletion type we have the same current relation of the drain side, which is also for the source sides. And for enhancement type MOSFETs, even enhancement type of MOSFET, both have the different relationship for the drain current as well as for the source current. And for enhancement type, we will try to cover the feedback configuration and the voltage divider biased circuits. And fundamental relations which are applicable still here in all type of FETs are these all devices are operated when there is a gate current is 0, and in this case we can find that because it is a unipolar device, so in this case current flowing through the channel is the drain current is equal to the source current. And for JFETs and for depletion type MOSFETs, we have the current relation like this one, and this is the Shockley equations, and so it we can find the value of the drain current when the VGS is given across the gate terminals, voltage is given, and definitely pinch off voltage and the maximum saturation current of the diode terminals is also given. And even we can reversely find the relationship when the diode current and the maximum value of the current and the pinch off voltage given, then we can even find the voltage at the gate with respect to the source terminals. And for enhancement, this relation is slightly different from this one, and here this relationship is current through the diode is equal to K coefficient and times the VGS and the difference with the threshold value. This is the minimum value of the VGS through which the current start to flowing, and it is again it is the nonlinear relationship of the control parameter due to the VGS. And for fixed bias configurations, this is the fundamental circuits, and as in this chapter, because this is a DC analysis, so for DC analysis purpose, capacitor C1 and C2 both are acting as a open circuit and shows the infinite impedance. And because our assumption is that current through the gate is 0, so voltage drop across this resistor RG is 0, So simply we can replace by this circuit. This is the simplest uh, circuits after taking the assumption that Ig is equal to 0. So definitely voltage drop across the gate is 0. So in this case, voltage supplying to the VGS is equal to, in this case, VGS is equal to minus of the VGG. This supply applying the potential uh, to the both this terminal VGS, and we can find through the KVL equations. And similarly, in data sheet are in due to the given parameter, maximum current through the drain and the pinch of voltage both are given. And next point is how to find the value of the VDS. So it is, these things are already covered in the last lecture. So we have to apply the KVL across in this loop. So this is so this is the simple. So we can apply the simple KVL here. This is the VDD, and we can find the values of the VDS. And VDS is, in this case, is equal to voltage supply, main voltage supply minus voltage drop across the resistor R, which is RD, which is ID times RD. So this is the voltage relations, and this relation is still applicable. This Shockley equation is applicable. VGS over VP is square. So this VGS in this case is equal to the this DC source, and the last point which are still applicable, VRS, voltage drop across the uh, source terminal, is 0. And definitely this analytically part will be applicable here, and we can even find these values by using the graphical method, because the behavior of the device is given. This is the some, this is the graphically blue color representing the behavior of the device. So this is the maximum current which is at when GS is 0, and this is the minimum value of the current when we apply the voltage across to the pinch of voltage, which is -8. And at the half value of the pinch of voltage, we find that current is the quarter. For example, this is the example situations. And definitely if the voltage is given something which is -2, then we can find correspondingly current at Q point is this one. Q is the point which is operating, which is lying on this line, blue line. So if we select some Q point here, we can change this point accordingly if we change the voltage across the VGS. So then draw the vertical line as well as horizontal line, then this is the current corresponding to this Q point, and similarly if we draw the vertically here, then this is the VGS value. And definitely these points can be found through the graphical methods. So next is the self-biased configuration, and in the self-biased configuration, this can be achieved through the values of the RS, which is given here. And again, it is a DC analysis. For DC analysis, so capacitor C1 and C2 still open here and showing the high impedance, and again voltage drop across this RG is equal to 0 because there is no current in this one, in the gate. So so we finally can say that current through the gate terminal is 0 ampere, and so this is simply we can replace this circuit with this one, and if we apply the KVL here, that VGS is equal to minus ID RS, voltage drop across this resistance, and ID and IS have the same values, and this is an important relation which will be applicable when we find some graphical or some literally way to find the values of the VGS. In the last case, VGS is equal to the DC source. So value of the VGS can be changed when we change the value of RS, as we discussing in the last slide. And again, the relation, so and other relations can also be found here, that for example there is some source like VDD, which is this one, and applying the some KVL maybe in this direction, maybe in this direction, is equal to minus VDD equal to plus VRD plus VDS, voltage between the drain and the source terminals, and the voltage dropped across the source resistor is equal to 0. So in this case, VDS is equal to VDD minus VRD minus VRS, and we find that this is the DC source, and this is the this voltage is equal to the drain current time the resistance across the connected with the drain terminals, minus ID or IS, which is the same values, and RS, and simply we can say this VDS is equal to VDD minus ID times the RD plus RS. So this whole combination is actually controlling the voltage across the VDS between these terminals, and other relations which are also applicable here to find the drain current is equal to the drain maximum current in saturation is equal to minus VGS over Vp, where VGS is the voltage between the gate and the source, and Vp is the pinch off voltage, and this is the some maximum value. And we find that this is equal to this value, so ID is equal to IDSS 1 minus, so minus ID RS over Vp. So this is the relation. So this negative make this a positive, and we find that so drain current is equal to the maximum drain current 1 plus ID RS over Vp whole square. And if we simplify this relation, we can find uh, definitely this 1 Vp plus ID RS over Vp the whole square, and if we scaling the terms and multiplying on the both side by Vp, and after simplifications we can say that this ID square term plus some coefficient with the simple value, and this is the quadratic behavior showing, and K2 are the parameters of simply here. So this is the behavior, quadratic behavior of the current through the diode. So mathematically we finally say that the voltage, because uh, gate voltage is 0, and VGS, which is very important relation, is equal to ID RS, and even we apply some analytically way and also for the graphically situations. And next is the VDS, which is already derived in the last slide, ID times RS plus RD. And this relation, which is the another form of the relation, can also be drive 1 minus VGS over VP, and if we replace this by this relation and after simplification we can quadratically solve this value. So these are the situations here, and again VS, which is the voltage drop across the resistance, ID RS, and that's all. This is the and which is VD. For example, if we want to find the values of the VD, which is equal to VDS plus VS. So this is can be simplified because we can find VDS through these relations and VS through these relations, and this is the analytical way to find these values. And so uh, this is the self-biased lines. So in this is the graph which is showing for the relation that which is satisfy these relations. Saturation current 1 minus VGS over VP and a whole square. And we find that this is the point when there is a maximum current. Maximum current at this point, drain current is 0 when VGS is equal to this one. And similarly, when we apply VGS is equal to this one, so definitely VGS is equal to this point, and this drain current is 0. And other relations which are applicable here, for example, VGS is equal to minus ID RS, and this is the line which showing the behavior of this line. And so these two behaviors where the intersects are the Q point or the solution set, where the this blue line is the behavior shown in this way, and similarly this solid black line is behavior is modeled by this one. This is already defined in the last situations. And for example, if we find that diode current is equal to the dss by 2 half of that one, then VGS is equal to minus ID RS is equal to minus IDSS RS divided by 2, half of that one. Say for example, if we selecting the point of half current is here, then corresponding voltage is here. So this is the point of that one, and this is the Q point, and we are interested to find the solution set for these Q points. And next is the example. In this example we want to find the, so first of all you have to observe the self-biased configuration. So how we can guess this is self-biased configuration? Because there is a resistors 1 kilo connected between the source and the ground, and this 1 mega ohm is the RG, and definitely effect of this RG is the 0 or minimum. For example, if we are talking about current in milliamperes or amperes, so current in this gate is in the, for example, in the range of nanoamperes. And for this network we have to find the value of the VGS at Q point. Q point is fixed when RS value of the RS is fixed, and we have to find the drain current at that point. And similarly VDS and VS is directly find through the situation when we have the current of the drain, and then VG, which can be easily find after finding the VGS value. So this is the situation we have to find the values. So, and also it is very important that maximum drain current is given and Vp is also given. So how to find the value of the VGS? First point, for example, if we want to find the value of VGS in the given circuit, which is equal to minus ID RS, and for this case, so in this example we have to find the value of the VGS, first part VGS at Q minus ID RS, and first of all we have to suppose that drain current is 4 milliampere and RS is 1 kilo, so VGS at for this particular situation is equal to minus 4 volt. This is the situations. And similarly, if we select some other value of the current, drain current is 8 milliampere, in that case VGS at that particular point is equal to minus 8 volt. So this is the situations for different values of the current is we can find through the different values of the drain current. From this type of discussion we can clearly see that for any value of the current it always follow the some straight line values of the VGS, and similarly it is important to find the value of the VGS. If we select any value of VGS, then we can find the value of the ID correspondingly, and this is the situations we discuss here, and this uh, and this graph is the VGS is equal to minus ID RS, and this is the graph which are showing here. And if we select, if we find the characteristics of the JFET, which is this is the behavior of the device, this is the behavior of the device, and this is the relation which is against the VGS minus ID RS, and this is the point where these two lines are intersect, and this is the solution set at the Q point for the given situations. And from the graph we can see that this is the value of the value is minus 2.6 and correspondingly current is 2.6 milliampere, and by using these values we can, so first point we have to find the values of the VGS at Q point, which is the intersection of the behavior of the device and the behavior of the VGA of the behavior of the VDS, and the intersection point gives the values of the VGS at that particular point, which is 2 point minus 2.6 milliampere. And next part is the corresponding current through the drain is again it is equal to 2.6 milliampere, and this is the volt. And next, C part, in which we have to find the values of the VDS for the given circuits. So we derived many times this relation, which is equal to ID, and it is RS plus the RD. So after substituting these values, which is 20 volt minus 2.6 milli times the 1 kilo plus 3.3 kilo, and the values of the VDS is equal to 8.82 volt, and values of the Vs is equal to ID Rs, which is equal to 2.6 milli, and it is 1 kilo. It is equal to the 2.6 volt. And similarly, E part, what are the values of VGS? It is 0 because it is the current is 0, so it is directly connected to the ground. And F part, we have to find the values of the D terminal, which is equal to the VDS. VDS is equal to the VD minus VS. So when we take this VS on the right hand side, this is positive, so it is 8.82 plus 2.6, so this is equal to 11.42 volt. So this is the values we have to find. And the next problem is, when we change the values of the RS for different values of the RS for 100 ohm and for 10 kilo, what will be the situation? It will be the next part. So for the given circuit, we have to find the values of the VGS, IQ, and this is the final result. And to find these values, and in the graph there are two Q points for different values of the resistance. For example, if we select the resistance is 100 ohm, then this is the Q point, and corresponding to this Q point, this is the relation, and this is also the relation which is applicable for different values of ERS, and it is for the 10 kilo, so slope is changing. So for this Q point, which is maybe a Q1, 6 milliampere, and similarly if we find the next, it is showing the 0.4 milliampere. For example, for the first case, we can find that ID at Q point for the first case is 6.4 milliampere. It is actually approximating, this is the from the graph, and correspondingly VGS at that particular point, maybe Q1, is equal to minus 60.64 volt. And similarly for 10 kilo, I drain current is 0.46, it is approximated equal to a point, even 0.5, and similarly VGS at that point is equal to minus 4.6 volt. So these are the two different values. So this how we can control the values of this one. If we require the more current to flow through the diode, then we have to take the values of the resistance is lesser, as compared to if we require the uh, less current to operate, then we have to increase the values of the RS. So this is the values of the RS, how this vary, it is very important. So voltage divider biased circuits. So this type of circuits we already covered in the BJT DC analysis in chapter 4. So that is similar to that one, but here we are replacing with BJT by the JFET. So fundamental uh, concept related to the JFET, that it is operating with the gate current equal to 0, and as BJT it is operated by the base current, but in JFET these are operated by the voltage VGS. So this is again a very important concept, and again C1 and C2 both are the coupling capacitors, or in DC analysis we can replace by the open circuit because it shows the maximum impedance or infinite impedance. And so in this case behavior of the device is same, and we can use the same situations and same characteristics as studies before. And in this case VG, with the variation of VG we can find the variation in the current. And as we see in the voltage divider case, in the uh, last case, it is almost similar to the BJT chapter 4. So in this case, if there is no current flowing here, so we can separately represent by this one, and it is just a series resistance R1 and R2, and voltage across this terminal is VG with respect to the ground, and this is the applied voltage, which is VD. It is a single battery, and voltage of this one, because these are in series, we can find the voltage across the R2 by simply by using the voltage divider rule. So what is the voltage divider rule? Actually voltage across this resistance is equal to the ratio of the voltage ratio of the resistance of R2 to the total of the resistance time the input voltage, which is in this case is VDD. And similarly, what is next one? For example, so this is the loop. For example, in this loop we are just applying the KVL, and we find that, so first of all we have to repeat the concept of polarities. So this terminal of resistor R2 is positive with respect to this one, and similarly this is positive terminal and this is negative, and similarly voltage across the RS is again upper terminal is positive, relatively positive with respect to the lower terminal. So we just apply the KVL. So KVL is just showing here that maybe we can write in this form: minus VGS minus VG plus VGS plus VRS is equal to 0. So VGS is equal to VGS is equal to VG minus VRS, and which is equal to the ID times the resistance. And there is a Q point related to these parameters. If we are fixing these parameters off, then there is some Q point. And how to solve this one uh, in a graphical way, which is a simple situations. In this okay, first of all we review there are three steps. First one, plot line by plotting the 2 points. For example, in this case we see that this blue color representing the behavior of the GFET. In this case we are using the N channel, and this is the fundamental situation. When VGS is equal to VG, then current is equal to 0, and similarly VGS is equal to 0, then ID is equal to Vg over. And the second relation we find here, there are two. Actually, this Q point is the intersection of the behavior of the device and the this characteristic equations. And these characteristic equations we can just use as in the previous case, that VGS is equal to VG minus ID RS, and this is the extreme points. When VGS is equal to VG, in this case ID current is 0, and when VGS is 0, in that case current is equal to this one, and this is the some minimum point, and this is the y-intersect point. And when it is intersecting the blue color line, which is the behavior of the device, this is the Q point. So ID assesses the maximum value, and Vp is the pinch of voltage, and ID is the diode drain current. So some other fundamental relations. First of all, we see from the diagram that if there is a battery VDD, it is just to understand, otherwise circuit is complete. So if we apply the KVL here, we can find this one. This VDS is the source, and all the voltages, for example VDD is equal to voltage drop across the resistor S and voltage drop across the VRD, and similarly VDS voltage drop across the drain and the source terminals, and this is the way to find this one. And other point is that difference between the voltage of this terminal VDD, for example second step is difference between the VDD voltage and the voltage at the diode terminal is equal to the drop across the diode resistors RD. Uh, so it is not diode, it is the drain connected resistors VRD, and in this form we can find the voltage of the drain terminal is equal to the VDD minus voltage drop across the RD. So this is the relation. And the last point is uh, Vs minus 0 is equal to the voltage drop across the resistor Rs, and this is the simple this one, and this is the simple situation, and we are this is the same current flowing through R1 and R2, and simply we can find by using the Ohm's law Vd is over the sum of their resistance, and that's the four relations are we can derive easily from this circuit. As we find the characteristic equation for VGS is equal to VG minus ID RS. So for if drain current is 0, then VGS equal to VG, and this is the this starting point of the line. And similarly for VGS is 0, so I am talking about this vertical line axis. In this case, drain current can be calculated through Vg by Rs. If Rs is high, then this is the lowest point. If Rs is less as compared to, for example, Rs2 is less, then this point is higher than this point. And similarly, if both lines, the behavior, these lines behavior is modeled by this one, and this blue color is the behavior of the device. And these are two intersection points on the blue lines. These are two Q points. We are talking about the two Q points for different values of the RS. If RS value is high, then this is the Q point, and it is belong to this region. And similarly, if RS is relatively low, then Q point is high. And even we can adjust this Q point by this one by changing the values of RS. So again, it is the designing part, and definitely um, maybe we will numerically not cover, but you can find the different Q points by changing the values of the RS. Though this circuit is given for values of R1, R2, RD and RS 2.1 mega and 270 kilo and 2.4 kilo and 1.5 kilo respectively for RS, and there are three coupling capacitors for DC analysis. These are acting as a maximum impedance and opens, so we are not including in the DC analysis. And we have to find the values of the ID, VGS, VD, VS, VDS and VDG. These are parameters which are required to. For the transfer characteristics for when drain current is the quarter, in this case VP is -4, so VGS is -2. And similarly we can find, we have ID when it is quarter to the maximum value. For example, 8 milliampere divided by 4, it is 2 milliampere. And then VGS at the half of the pinch of voltage is -2 volt. So, and from the we can find the values of the VG, it is VGS, by using the voltage divider, as IG is equal to 0. It is just 270 kilo divided by 270 kilo plus 2.1 mega. You should take the same values. For example, it is maybe 0.27 mega times the total voltage which is given by. If we find that this is equal to the 1.82 volt, so Vg for the given parameters is equal to 1.2 volt, and similarly Vgs is equal to Vg minus voltage drop across the RS resistance, which is ID, times 1.5 kilo. So Vg is 1.82 minus ID and 1.5 kilo. For different values of the drain current, for example, for ID is equal to 0, in this case VGS is 1.82 volt. For VGS is equal to 0, in this case drain current is 1.82 volt over 1.5 kilo, that is equal to 1.2 milliampere. So here we find that these relations which are very important. VGS is equal to 1.82 minus ID times the 1.5 kilo, and for different values of this one. And if we see here that if it is so this is the behavior of the JFET, and this line representing the behavior for the load line. So this is the Q or quotient point, and if we find these values, current of the diode drain at Q point is 2.5 milliampere, and similarly VGS at this point is equal to minus 1.8 volt, and these values may be vary. 1.7 is and around about these values. So these are the values related to the Q point. And next is we have to find the VD. So first part is clear. In the first part from the graph we find that ID at Q point drain current is 2.4 milliampere and VGS at Q point is minus 1.8 volt. So in the B we drive these relations, and definitely we can drive again for the problem purpose to solve the problem. So it is 16 minus 2.4 milli times the 2.4 kilo. So this is equal to 10.24 volt. And similarly for the C part, Vs is equal to this current time the resistance, which is 2.4 milli and times the 2.4 kilo, and again it is equal to 3.6 volt. And similarly the D part, VDS is equal to VDD minus ID, and the sum of the resistance connected with the drain and the source. And after substituting we find that it is 6.64 volt. And similarly in the E part we want to find the value of VDG, that is equal to VD minus VG, that is equal to 10.24 minus 1.82, that is equal to 8.4 volt. And these are the problems we find for the voltage divider circuit. In this lecture we covered the fixed biased configuration. Just review this topic, and starting with the examples of self biased configuration, and then the voltage divider biasing, and complete with the examples, and you should try different type of examples by using these type of configurations.